So in the third video of SLO9, we'll be looking at what happens when enolates react with carbonyl electrophiles. So we've chosen a simple example here, where we have an enolate. We've probably made it by deprotonation of the alpha carbon of the corresponding ketone. And that we would think about the process where this enolate reacts with, in this case, an aldehyde, but you could imagine other carbonyls too. So as we've been learning all throughout the semester, this carbonyl carbon here is electrophilic. And we've learned in the course of the first two videos in this SLO, this alpha carbon of the enolate is nucleophilic. So we could think about simply connecting this carbon to this carbon. But we know that that's not the only kind of bond change that happens in this kind of a process. We would need to break the CO bond. So it looks to me like we've done an addition reaction, just like we've seen for other kinds of nucleophiles with carbonyl electrophiles. And then the last thing that I want to introduce here is that if we're starting with the major resonance structure of the enolate, where there's an O-, we'll also need to show reformation of the CO double bond. If we did not include this last arrow, we would have had a positive charge on a carbon here, which would be like the minor resonance structure of a carbonyl. So basically what we're trying to do is describe the most stabilized set of electrons in the compound that we'll be making. So this is an addition. I'm just going to follow my arrows and make a new CC bond. The rest of the structures all stay the same. There's my carbonyl. And the rest of the product. So we've made a new carbon-carbon bond. Anytime we do that, we're always going to be a little concerned that we made sure we attach the right atoms. Because we don't draw carbons explicitly, it's easy to get confused. So what I'm going to do is trace this electrophilic carbon onto the product. It's here. And then I'm going to do the same thing for my nucleophilic alpha carbon. So that's going to be one carbon removed from an oxygen. That's here. So it looks to me like we've actually done the right bond-forming reaction. And that's what we would expect to see. Just in addition, this looks very much tetrahedral intermediate-like, but there's no group that I can reasonably eliminate, and so we would stop here. So these kinds of reactions are very common. People use them all the time to make carbon-carbon bonds in a variety of contexts, ranging from simple molecules like this one to very complex structures. Moreover, if you actually delve into enzymology, you'll find that there are several important classes of enzymes that actually perform very similar kinds of reactions in biochemical settings. So how would you actually use this kind of an enolate reaction with a carbonyl electrophile to your advantage in making structures? Well, there's a few things we notice. One is that we can't start with an enolate. We always need to actually think about generating them. So that means we'll have to have a step for some kind of reaction you do in a lab that's a deprotonation, which we've talked about in the previous videos. The other thing that we would need to consider is the structure of the product, right? So here, we're going to have a hard time isolating this compound because of the negative charge in the product. And so here we would introduce a workup to add a proton to this negatively charged oxygen. So in a practical sense, or maybe for synthesis, we would represent the same kind of a reaction where the important part is the CC bond forming, but we would do it in three separate steps. So we would start with our ketone. And first, we would deprotonate it. So we could choose any kind of base that we want. I'm going to arbitrarily choose LDA. And then once we have our enolate, we would add the electrophile. So that's our aldehyde in this case. It doesn't have to be an aldehyde. And then in the final step, we're going to do a workup. So this looks a lot like enolate alkylation, which we saw in the second video here, where these two steps are make the alpha carbon nucleophilic and then add an electrophile. All we've changed is whether we're using an alkyl halide or whether we're using a carbonyl. What's new when we use a carbonyl as an electrophile is the workup, and that's because of the nature of this oxygen after the addition step, right? So you don't need a workup for an enolate alkylation, but you do for these kinds of other reactions. So if we did all three of these steps in sequence, right, so not all at once, three different stages, we would end up with a product that looks just like this, but with an OH group instead. Okay, So one thing that I want to point out here is that we could name this product. So if I want to solidify our use of the terms like alpha and beta, we could call this a beta hydroxy ketone. And what we mean by that is that we have a ketone, and there's an alcohol or a hydroxy group at the alpha beta carbon to the carbonyl. So we actually use these alpha, beta, gamma, delta, etc. nomenclature to describe the placement of a functional group relative to a carbonyl, like in this case a ketone. Okay, so let's look at a couple of other examples of this kind of reaction. So we could also look at cases where we have two different enolates that can form. And like we discussed in the second video in this SLO series, depending on what we wanted to do, we would use basis to make decisions about which enolate can form. So here I've got an alpha carbon at this position, an alpha carbon here. Both of those could be deprotonated, so I have the issue of regiochemistry. If I wanted to do a reaction where I actually placed one of these hydroxy groups beta to the carbonyl on this side, so basically if I wanted to make this carbon nucleophilic, so I'm wanting to make that a carbon nucleophilic, I'm going to need to choose LDA because it's the kinetic base that I need. Of the two possible enolates I could form, the one I'm wanting, for whatever reason, is the less stable of the two. So I need to be able to enforce forming it using rates. All right, so the way we would do this would be first, again, LDA. Second, we'd add some kind of electrophile. So I'll choose a different kind of an aldehyde here. Compound called benzaldehyde, so a benzene ring or a phenyl group attached to the carbonyl this time rather than a methyl. And then we're going to need to work on it. Okay, so you can see the pattern from our example here, and I'm just going to highlight again the new CC bond it forms right there. That's the bond we made. What I'd like for you to do is predict the product for this reaction. So after all three stages, what would you expect to isolate? So go ahead and pause your video and do that problem now. So you've had a chance to think through this problem where we're predicting a product, and I hope that you approached it in the way that we usually approach these problems, where we're identifying reactive sites. That simplifies the process of thinking about what kinds of bonds might form. It also solidifies your understanding about the relationship between structure and reactivity, which is an important framework for you to take forward in all of your classes that deal with molecules. So we already established we want this carbon to be nucleophilic. That was an arbitrary choice. Maybe we needed that compound for some purpose. And then we would need to think about electrophilic carbons, and we find that our aldehyde carbonyl carbon would be electrophilic, so I now need to attach those. So that means that I can effectively redraw this entire compound, because what I'm going to be doing is essentially functionalizing this alpha position. I'm going to substitute a CH for a CC. So I'm going to take a minute to redraw my framework for the structure. Okay, so what I've done is basically just taken this methyl group and moved it down so I have space to work. And the structure will look a little less weird. So now I know that this position was nucleophilic. And that means that my new carbon-carbon bond is going to be coming off from that position. So here's my new CC. And on the other side of that new bond is going to be the electrophilic carbon. So let me put my E in so I can template myself here. And that means that I'm still going to have my phenyl group attached to the electrophilic position. So there's my pH. And then finally, I'm going to reduce the bond order between the C and the O because I'm doing an addition. So I'll have an alcohol at that position, at the carbon that was electrophilic, right? So that's what makes it electrophilic, because I can break the CO double bond, for instance. And then finally, I know from the workup that I'm going to have a proton on that alcohol. So again, it looks like we're making a beta hydroxy ketone. Regardless of the kind of enolate or compound that we get an enolate from, along with the aldehyde, this seems to be a pattern, at least when we use aldehydes as our electrophiles. So a couple of things that I want to point out here in terms of pattern recognition. So when we're making these kinds of structures, we're always going to end up with an alcohol on the carbon that was electrophilic. And we're going to effectively substitute a CH for a CC bond on the nucleophilic piece. So that can help us to simplify these kinds of problems, especially as the structures become more complex. So we'll look at one more example in this section of the video. I'll give myself a little space here. So let's look at a cyclic ketone, like so. And let's react this with sodium hydride this time, because we have the two sides of my ketone are symmetrical. I have two different alpha positions, or two alpha positions, excuse me, but they're not different. They're exactly the same, so I'm not worried about enolate regiochemistry. And let's choose a different kind of an electrophile. Let's use a ketone here. So we'll use acetone. And then we know that we probably need some kind of a workup because we're using a carbonyl electrophile. We need to deal with the oxygen that's going to become negatively charged. So I can play the exact same game. I could choose either of these carbons to be nucleophilic. They're the same. I'm going to arbitrarily choose to make my alpha position on the right nucleophilic. So that means the first step I would deprotonate at this carbon, make an enolate. That would then react with the electrophilic carbonyl carbon. And then finally I do the workup. So let's see if we can apply this pattern to help us. That means that we're going to end up with another cyclopentanone. It looks like I'm just doing a substitution. Well, there's N, so I know that I'm going to have a new CC bond at that site that I think will become nucleophilic in the presence of a base. And then that other carbon on the other end is going to be my electrophilic piece. And that means that I'm going to have two methyl groups attached to the electrophilic carbon. And then finally I'll have an alcohol on that same carbon. Right? That's one of our observations. So that would be a putative product for this kind of a reaction. So I said we were going to do one more example. I'm feeling a little inspired. Let's do one more where we'll actually use an enolate from an amide, which it turns out you can also form. We haven't seen any examples of that yet in the video series, but I want to make sure that you do see it. So let's choose, I don't know, I'm feeling a little creative. Let's choose this compound. And we want to make this product. Okay. So here what we're going to do is actually try to figure out what kinds of reagents we need. And we need to do this in a few different steps. Based on the structure, we still see that we have this beta-hydroxyamide now, or you could think about beta-hydroxycarbonyl. So probably I'm using some kind of a carbonyl electrophile. All right, so this is beta from carbonyl electrophile. This pattern of seeing the carbonyl and the hydroxy group beta to it is usually indicative of having made a CC bond from a carbonyl electrophile. And moreover, I know that the CC bond that I would have made in that reaction has to be the one that runs between the carbonyl and the alcohol. Right? So I'm going to connect the alpha position to what will become the beta position doing this kind of reaction between an enolate and a carbonyl. So if I have the structure of a product, I can work backwards, where I know that if I find the alcohol that was, this carbon was the electrophilic site, and then the new CC bond will be the one that runs toward a carbonyl. Okay. So what we know we need to do is make an enolate. So the pKa of our proton on the only alpha position here is, again, about, let's say it's about 25. Right, so these are also a little bit more acidic, I'm sorry, a little bit less acidic than in ketones and aldehydes, like we saw with esters. But LDA or sodium hydride is still basic enough. We'll use LDA here. So the meat of the problem then is figuring out what the structure of the electrophile was. And because I know that this CC bond is the one that was forming, and I know that the alcohol is attached to the carbon that was electrophilic, I probably can draw this 1, 2, 3, 4 carbon piece like so. this carbon here on my chain would be where the alcohol ends up. And so I know that in the starting material, to make this carbon electrophilic, I probably need some kind of a carbonyl. So I have a carbonyl, and then the last question is what else is attached to my carbonyl carbon? So far I've only defined one substituent. Well, I'm going to look at the beta carbon. So I have this alkyl substituent, I've got my alcohol, but I also have an implied hydrogen. And that tells me that I had an aldehyde in my starting material. All right, and then the last thing we know is because we're getting an alcohol as a final product rather than something that's O minus, I have a water workup step. Okay. So we've been able to see a couple of things in this last example. One is that you can make enolates from amides, and they work the same way. And we've also kind of developed a strategy where we could look at the structures of products that come from these kinds of reactions, where enolates react with carbonyl electrophiles, and work backwards from that product by figuring out where the electrophilic site was, that's where the alcohol is, and then which of the two CC bonds, or maybe three CC bonds, that spring from the beta carbon was likely the one that made. It's the one that traces back toward the carbonyl. Okay, so in the next section of this video, we'll be looking at a twist on this general feature of reacting enolates with carbonyls. In this section of our video, we'll be looking at a very different way of making new CC bonds, but using the same kind of addition chemistry that we've been discussing in previous sections. So in this case, what we're going to do is look at a reaction where we have an aldehyde. Remember that what we're doing is representing a set of compounds. So this structure doesn't mean there's only one molecule. It means that we would have some of this that we would have added to a flask. And we're going to dissolve it in water and add a little bit of sodium hydroxide, so a catalytic amount, a small amount relative to the amount of aldehyde present. And that we find that in these cases, we make products that look like this. So if you look carefully at this, you probably recognize some structural features. This looks like a beta hydroxy aldehyde. And because we're noticing this beta hydroxy carbonyl pattern, we can make some reasonable guesses about how this product formed. So I know that this carbon here, where the alcohol was, that could have been an electrophilic site. So I'm labeling in the product what these atoms were when as the reaction was happening and the product was forming. And that means that either this carbon or this carbon was probably the nucleophilic site. And if I look at what I'm starting with, I know that I have an alpha position here that I could deprotonate potentially and make it nucleophilic. So if I trace this structure onto this structure, I'm seeing this repeat right here, but attached to another unit through that CC bond. So it looks like what I've done is made this new carbon-carbon bond, and that means that our carbon here was nucleophilic. This sounds just like the reaction we were studying before. But you'll probably notice that this looks really different in terms of reaction conditions. First of all, we don't have two separate carbonyls, like a ketone and then an aldehyde. We just have an aldehyde in this case. And we don't have different stages. We don't have treat the compound with a base and then add some electrophilic carbonyl and then do a workup. We've just got this catalytic amount of base and water. So I think what would make sense for us to do at this point is try to propose a mechanism that's consistent both with what we already know about how enolates react with carbonyls, as well as how we can explain how this reaction is happening under a very different set of reaction conditions. So we'll go through the mechanism of the so-called Aldol reaction. And if you're good with names or words, which I bet you're getting better at after our sugar section, you might recognize aldehyde, kind of like aldose, and al, kind of like alcohol. So what we're describing are reactions where we make these aldehyde and alcohol containing products. So I'm going to start with our aldehyde structure. And when we talked about acid catalysis earlier in the semester, I said something like, if we're proposing mechanisms, try to use the catalyst in the first step. Well, we'll use the same idea here, even though we're using a base. So the sodium part is unlikely to matter a lot, so I'm going to represent this as OH minus. All right, so I've got a hydroxide anion. And I know from the structure of the product that I'm trying to explain a way where this carbon becomes nucleophilic. That's an alpha position. So based on what I already know, I'm probably going to deprotonate the alpha carbon. So I can show enolate formation as my initial step. And I'm going to show this in a way that will yield directly the major resonance structure of the enolate. So acid-base chemistry, before we actually assess pKa's, we always want to assume that this is reversible. And I would end up with a structure that looks like this. So this is my enolate and a water molecule. That would be the conjugate acid of my hydroxide. So I want to assess pKa's here. It turns out I did this in the first video, but we'll do it again here. So this pKa for my alpha proton is about 20. It's a little bit less than that for aldehydes. It's like 18, 19, something like that, but 20 is fine for an approximation. And we know the pKa of water. This is one of the ones that's really good to have memorized. It's 14. And that's not an approximation. It's equal to 14. So if we look at this acid-base reaction, the forward reaction is going to have a stronger acid as a product than the reverse reaction will, right? Another way of saying that is that this reaction, this acid-base equilibrium, will favor the side with the weaker acid, which is the left. So what we know is that this reaction primarily runs backwards. We've got a little bit in the forward sense, and then a lot in the backward sense. And we could even calculate a KEQ here if we knew the pKa of an aldehyde. If we assume it's 20, then the KEQ value is 10 to the negative 6. 14 minus 20 would be my exponent. So that tells me that this is not particularly favorable. This is definitely a reversible deprotonation. So here's one of our reversible enolate formations. This is very different from what we were doing with LDA or sodium hydride, where we were using a base that was so strong, we were essentially pushing this equilibrium all the way to the right. So what that means is that as this first step happens, we have many, 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 many molecules of our aldehyde and a tiny amount of enolate present, right? So a very small amount of enolate relative to aldehyde. That's important because if this enolate forms, it's now nucleophilic. And if this reaction were irreversible, there would be no electrophile present. All I would have were other enolates. Enolates don't react with other enolates. But because I'm doing this in a way where I've got small amounts of this relative to what I have left of my aldehyde to start, this enolate can find another copy of the aldehyde that hasn't been deprotonated. So I'm going to draw that here, and I'm going to turn it around. That's just for clarity in drawing, but it's still the same aldehyde we started with. And I know from the previous sections of this video that I can use my enolate nucleophile, so the alpha position, to do an addition to an electrophilic carbonyl like that of the aldehyde molecule that's still present. So that is going to give me, after the addition step, a structure where I've got a new CC bond now, which I'll highlight in red. Boom. And let's see, adding an enolate to a carbonyl carbon, going to have an alcohol at the electrophilic site, and then this ethyl chain will still be present. So that's, oops, not OH, sorry. So that's what we've got. Mechanistically, we still have O- though. We've just done the addition, and that means that the last step, I would need to figure out a way to put a proton on this oxygen, but we have a protic solvent. We've got a lot of water molecules present. We've also made a water molecule in the previous step, so we definitely have water around. So that's kind of like a workup. It's just not a separate stage of the experiment. It's happening whenever this O- species is forming. Okay, so we've got a protonation of our product, and that gives us our final beta hydroxy group. Okay. The other thing that we generate is hydroxide from deprotonating the water. So we actually regenerate our catalyst. That's good. So that mechanism makes sense in the sense that like all these steps are consistent with what we've seen before, either from previous videos or different sections of this one. And we're also seeing our catalyst regenerated, which is important. So in the next section of this video, we'll be looking at some of the specific parameters about reaction conditions that can impact what kinds of specific products form in these aldol processes. So if we look at the same reaction that we looked at in the last section of the video, which I'm showing here, one of the things I didn't mention is that typically we would run these reactions at relatively low temperature. Like you might actually have the reaction flask submerged in an ice bath. And that's actually going to impact how this reaction works. So under these kind of cold or ice cold conditions, which I'm going to label as ice bath in this particular case, we do end up with these beta hydroxyaldehydes. If we take the exact same set of reactants, but we reflux this or heat it up, we get a different kind of a product. Rather than a beta hydroxyaldehyde, we get a new alkene. So this we would call an alpha beta unsaturated, like a pi bond aldehyde. Alpha beta, so that shows me the two atoms that we're crossing. Unsaturated, like unsaturated fats, those have alkenes in them. Aldehyde. Sometimes people call these alpha, beta, enal, or enals, right? So enals, again, you can use your understanding of words and prefixes and suffixes. Your en sounds like alkene, al for aldehyde. So if we have an en at the alpha and beta carbon of an aldehyde, we could call it an alpha, beta, enal. Okay, so you get to decide which of these two products you make, the beta hydroxyaldehyde or the alpha beta enal, depending on the temperature that you run the reaction at, which is kind of crazy. So to help distinguish these two processes, which look very similar but give pretty structurally different kinds of products, we're going to call this process where we make beta hydroxyaldehydes, we're going to call this the Aldol reaction. And these kinds of products where we have a double bond, or CC double bond, rather than an alcohol in the product, we're going to call these Aldol condensations. That's a very poor looking S. So the reason we use this term condensation is because we know quite a bit about what's happening here. What I'm not showing you, but you could probably figure out if you've been looking at the structure pretty carefully, is that this appears to be this, where I've lost an OH group and a hydrogen from the alpha position. So I'm going from here to here by losing water. I'm not exactly sure how that's happening mechanistically yet, but that seems to be the formal or the net kind of structural change going from the beta hydroxyaldehyde to my alpha beta enals. And so condensation means removal of water from a structure to form a double bond. And that's exactly what we're seeing here. And we'll see other condensations. In fact, you have seen other condensations. Sometimes we call imine formation from carbonyls an imine condensation, because we're making a new CN pi bond and losing a molecule of water. So the next thing I would like for us to do then is to actually work out a mechanism for this aldol condensation process. It turns out that it comes from beta hydroxyaldehyde. So you can think about the aldol condensation as an extension or a continuation of the aldol reaction. And so what that means is that we're going to start our mechanistic reasoning from the beta hydroxyaldehyde. So that's what we talked about mechanistically in the last section of this video, or the previous one. So we'll start here. And we have the same reaction condition, so we still are going to have hydroxide, and we're still going to have water. And I need to decide what's going to happen. So when I think about the product structure, that double bond, I think about elimination. So that's typically how I make new CC pi bonds. And that means I need both a leaving group and I need a place where I can deprotonate. That's how E1s and E2 reactions work, the ones that you learned last semester. And I know that there's a place in the structure that I can deprotonate, because even though this is the product of an enolate formation and subsequent reaction with a carbonyl electrophile, I still have an alpha carbon. And that means I still have an alpha hydrogen. So that proton is still acidic. Its pKa is still going to be around 20, just like was the case with the aldehyde before I appended this other part of the group. And that means that I should be able to use my base to make an enolate. So I'm going to make an enolate out of the product of the Aldol reaction. I'm going to show the enolate in its major resonance structure, so there'll be a CC pi bond and an O minus. The alcohol group will be there. And so that's what I've got. This would be an intermediate. This reaction is probably reversible. If I know my pKa's, it's probably the equilibrium lies to the left, but I do make small amounts of this compound. So when I look at this structure now, something interesting happens, and I think would be a little bit surprising if you had only have your instruction about elimination for E2 reactions, and that's that we're actually going to eliminate the hydroxy group as it's on its own, which means we're using it as a leaving group, which we don't typically see. The reason for that is that we have this O minus already in the molecule. So if I do my elimination, then I'm making another O minus. That's not necessarily a big deal. My starting material charge stability is not much different from the final product here. So this elimination turns out also to be reversible. We'll talk more about that in the next SLO. And that gives us our CC pi bond and hydroxide. So like that. Okay, so this is an enolate formation followed by elimination that we're seeing, and that's what the aldol condensation comes from. So why heat? So the arguments here involve the use of thermodynamics, right? So enthalpy and entropy, and it's my understanding that those ideas weren't used in any specific ways last semester. So I'm not going to necessarily try to use them now to explain this, except for to say that heat actually makes this final elimination more favorable. So I'm choosing my words carefully. I don't mean faster. I mean the equilibrium constant is going to be larger, favoring the products at higher temperatures. So our elimination, more favorable at higher capital T for temperature. Okay, so we've gone through our Aldol condensation mechanism. Remember, it's both the Aldol reaction, so enolate formation, addition to an aldehyde electrophile, right? Protonation of O minus, those three steps, and then these two. That's the whole mechanism for the Aldol condensation reaction. So in the next section of this video, we'll be looking at a few problems where we predict products and such for both Aldol reactions and Aldol condensations. So let's look at a couple of problems here. We'll work the top one first. So we have an aldehyde with just a methyl group, lithium hydroxide as a catalyst, and then we're actually using water as a solvent, and we're trying to keep this reaction cold. So we might be using like an ice bath, for instance, to cool the reaction as it goes. So there's a few things that I want to decode out of this set of essentially context, so I know what kinds of structural changes I'm going to expect. The first thing I'm going to look at is the temperature information. So this tells me that I'm doing an aldol reaction, not a condensation. And that tells me that my product will have an alcohol in it, a beta hydroxy group. Otherwise, I'm going to treat this the same way that I've treated all of the examples that I've been looking at in this SLO, where I'm looking for a place to make a nucleophilic carbon adjacent to a carbonyl. And in our structure here, that turns out to be the case. I've got my alpha carbon, I've got some base, I'm going to do a reversible protonate or deprotonation. You'll also notice that I only have the one carbonyl species, so that tells me that I'm going to be doing essentially what's called a homodimerization. So I'm going to make a dimer, or two units connected, that is composed of the same units. That's what the homo part means. So that tells me that my carbon here will be nucleophilic, and another copy of this molecule, my carbonyl carbon, will be electrophilic, and that will give rise to a product that looks like this. So just to check my work, I have a beta alcohol group. Good. That's what I would expect under cold conditions, right? I should see double the number of carbons that are represented in this structure. So 1, 2, 1, 2, 3, 4. That looks good. And then just another reminder that the way we made this CC bond here, this is electrophilic, this was nucleophilic, and the new CC bond is the one that is adjacent to the carbonyl and is attached to the alcohol carbon. Cool. So that all looks good. In our next problem, we have to do the same kind of a thing where we look for context. And here we're actually told we're running this reaction at reflux or, with a warming bath. And this tells me I'm doing a condensation, which means that I'm going to have an alpha-beta alkene, not an OH group. The other thing that I notice is I've got different kinds of solvents and bases now. So I don't have water, I don't have like a hydroxide. Doesn't matter. Well, the mechanistic reasoning that we did earlier tells us it does not, because I know that my solvent needs to also be a weak acid, right? We used water to protonate an O- intermediate in our mechanism for the Aldol reaction. Methanol can do that about as well as water can. Moreover, NaOMe is actually like a source of OMe minus. And that tells me that I have a weak base, or a relatively weak base, just like hydroxide. So the pKa's for methanol is about 15, just like water is 14. That means that OMe minus is about the same base strength as hydroxide, which means I can deprotonate my, in this case, ketone, but only a little bit, right? So I've got one of those reversible enolate formations. So my next step at this point, after I've decided some kind of a reaction can happen, and I know what kinds of structural features I'd expect in the product, is to look for where the reaction will happen. So I've just got the one species, this aldehyde. We're going to make another so-called homodimer. And that means that I'm going to need to find both an electrophilic site and something that can become nucleophilic within the structure. So it looks to me like I have two alpha carbons. They're the same as each other, so I get to choose where my nucleophilic site is. Okay, there. I like to choose the right-hand side for some reason. And then in another copy of this molecule, this carbonyl carbon would be the electrophile. So remember, it's not that in this structure of a single molecule, you've got a nucleophilic site and an electrophilic site. It's that this drawing represents many molecules of the same structure inside your flask. So I know in the products, I'm going to have to connect E from one of my copies to the end of my other. So I'll have, shouldn't have drawn that on the seam. Okay, and then I've got something like that. I'm going to, well, let me just choose similar notation, so I'll write CH3 instead of methyl. Try not to mix things up here. Okay, so I need to figure out where my alkene goes. This must have been my nucleophilic carbon. Here, this would have been my electrophilic carbon. Okay. So that means this is alpha, beta, so my double bond goes there. And then I'm going to count carbons, make sure I'm good. So 1, 2, 3 in my starting material times 2, because 2 of these molecules are going to react with each other. 1, 2, 3, 4, 5. Uh-oh, I'm missing a carbon. Well, where did it go? This is one of the reasons why labeling your roles is helpful. The electrophilic carbon has 2 methyl groups, and I've only got 1 methyl group in where that carbon ended up in the product. So I know that I need to add 1 more methyl. Okay. So let's look at one other problem here, and here we're going to introduce a small wrinkle. So let's choose a cyclic ketone. Doesn't have to be cyclic, it's just kind of convenient. And let's gussy it up a little bit. We'll put some methyl groups in and things like that. Okay. And so let's now treat this with benzaldehyde, sodium hydroxide catalyst, and let's use ethanol as our solvent. And we're going to heat this up. Okay, so a couple of things that seem to be different here. We have ethanol as a solvent now rather than methanol or water, so that might be different. I don't know. We've also got another carbonyl. So we have 2 different carbonyls, and we have these conditions that give us reversible deprotonation. So it sounds like we're kind of mixing things here. It sounds like these problems we did at the very beginning of this video where we were looking at like stages. Treat the compound with LDA, then add an aldehyde, da-da-da. In the Aldol reaction, we're dumping everything together, so like how do we actually solve this type of problem? Well, first, let's do our context analysis. Hot tells me I'm doing condensation. Hot, yes, of course, hot goes to hot, no kidding. So alpha beta alkene. All right, ethanol, is this going to work for me? Well, it's an alcohol group on an ethyl chain, so it's going to be very similar to methanol and relatively similar to water. So this is fine. Protic solvents, methanol, ethanol, water, isopropanol, whatever, they'll all work for us. I have a base, hydroxide in this case, but now we need to think about our carbonyls. How is this going to work? Well, I can assign roles. So I have two possible electrophilic sites, the ketone and the aldehyde. And now I need to find places that I could make nucleophilic. So I'm thinking about alpha positions that I could deprotonate. Well, I certainly have an alpha hydrogen here. So that means that our carbon here could be nucleophilic. That's a possibility. The other carbon flanking the ketone here has no alpha hydrogens, so it doesn't matter whether there's a base or not. This carbon can't become nucleophilic. On the other hand, I could look at my aldehyde, and so I need to remember what pH stands for. This is one of the reasons why acronyms are okay, as long as you can visualize what they mean. So pH is a benzene ring. And if I look at the actual structure here, I know that there is no proton attached to this alpha carbon. So when I actually do my structural analysis here, I find that there's only one carbon here that could become nucleophilic under these reaction conditions. That's simplifying. That makes my life a little bit easier. And now I need to decide, well, if this enolate forms, I'm only going to get small amounts of it, so I'll still really truly have two possible electrophiles, the aldehyde or the ketone. And now I need to decide which of those two is more electrophilic. We've played this game before many times this semester. And if you think back to SLOs 4 or 5, you know that aldehydes tend to be a bit more electrophilic than ketones because they have less hyperconjugative donation. And that means that we can reliably predict that this nucleophilic site will react with this electrophilic site. So another way of saying that is that this site is more electrophilic. And that gives us a hint about what kinds of products will form, where I'll connect this nucleophilic site to this electrophilic site rather than making a homodimer where two of these molecules react with each other. So what we're looking at here is an aldol condensation that we're making a heterodimer. Sometimes these are called mixed aldol reactions, where we're actually going to take two different kinds of building blocks and put them together into a single structure. So I'm going to follow my pattern where I know that the nucleophilic molecule will be represented in its entirety again. What I'm doing is effectively substituting at the position that I decided to make nucleophilic. So I know I'm going to make a new CC bond to this carbon. So I'll draw that new CC bond in. Here we go. And then I'm going to end up with, the benzene ring is not going to change. I'm going to put it back as a phenyl group now, or an abbreviated group rather. Okay, so my nucleophilic site was here. My electrophilic site was here. I know that this reaction was run under hot conditions, and that means that I'm going to have a double bond between those two spots. So I do the elimination step. Okay, so we've now seen an example of a mixed aldol. And it turns out that we saw mixed aldols at the very beginning of this video. I just haven't been calling them that yet. Okay, so in the last section of this video, we're actually going to be looking at a situation where it really truly is the case that your nucleophilic site and electrophilic site are within the same actual single molecule, and what happens in those kinds of situations. In this last section of our video, we'll be looking at what happens when we actually allow an electrophilic and nucleophilic part of the same structure react. So this is going to be an intramolecular reaction, right? We're going to end up making a ring because there's no other way for two reactive sites within a single molecule to react. They have to basically take the whole molecule, wrap it around, and then make the new bond. So the way we'll look at this initially is through an example with this so-called dialdehyde, so two aldehydes in the structure. And there's 1, 2, 3, 4, 5, 6 carbons. That will be important for us in just a minute. So remember that there's 6 carbons. So we know reaction conditions. We've got some catalytic potassium hydroxide, methanol as a solvent, and we're going to heat this up. So that tells us a few things, right? We're doing an aldol reaction of some kind. We're going to be able to reversibly make enolates here. And we know that because this reaction is being heated, that we're going to do a condensation rather than a reaction. So that means that we would expect an alkene in our final products rather than a beta hydroxy group. So what's left for us to do is decide which sites are actually reacting. So either of these two aldehydes could be the electrophilic site, and are there any places that could be nucleophilic? Again, I'm going to look for positions alpha to those carbonyls that it could be protein. So that means that like this site here, which has a proton, could be nucleophilic. This one too, electrophilic site, electrophilic site. How do I decide? Well, if you're paying attention to the structure, I don't have to. This is a symmetrical molecule. So this aldehyde is exactly the same as the one on the left. So really what I would need to think about then is that like if this carbonyl is electrophilic, it can't be the case that this hydrogen will also be removed and make the carbon nucleophilic. Either the carbonyl is a nucleophile or it's an electrophile. But for a given reaction, it's not both. So that means that I can decide one of these aldehyde carbonyls will be the electrophile, the other will have a nucleophilic alpha position. I'm going to show that like so. So here we go. That means that I now know that this carbon here is my nucleophilic site. And I'm going to make a ring when I connect my nucleophilic carbon to my electrophilic carbon. What size ring? This is going to be hard to figure out. I don't know. I'm going to have to draw a bunch of stuff and like, oh, I don't know. Turns out this isn't so bad. I'm going to number my carbons. So I'm going to say my electrophilic carbon here is 1 because it's the end of the chain. I can do that. So, and then I'm going to start numbering back toward the nucleophilic side. So 1, 2, 3, 4, 5, and then 6. Okay. So I'm going to look at the numbers between the electrophilic carbon and the nucleophilic carbon, and I'm going to basically think about the difference. So I'm starting at 1, I'm ending at 5. That's going to be a 5-membered ring. Okay? 1, 2, 3, 4, 5. And there'll be a new bond between E and N. So that means I can just draw a pentagon. 5-membered ring that looks like that. I get to decide where carbon 1 and where carbon 1 is, rather. I can place it anywhere in the ring to start because all that matters is relative to like where carbon 1 is, where everything else goes. So I'm going to make the decision that carbon 1 is at the very top of the ring, and I'll number around clockwise. So carbon 1, we know, is going to no longer be a carbonyl. We know that carbon 1 is attaching to carbon 5, and we know that carbon 5 is attached to carbon 6. So that means that on carbon 5 in my ring, I need to draw a carbon coming off of the ring. Okay, so, and then I also know that on carbon 6, because I chose carbon 5 as my nucleophilic position, I'll still have a carbonyl. So I have an aldehyde in this case. Carbon 5 was my nucleophilic site in the reaction. So I'm going to put that onto my structure also. Carbon 1 was my electrophilic site. And then the final thing that I know is that because this is a condensation, that I'm running this under hot conditions, that I'm going to have not just a new single carbon-carbon bond between the electrophilic and the nucleophilic site, it will be a double bond. That's the alpha-beta alkene. So I know in the final product I'll have 2 bonds between carbon 1 and carbon 5. Okay, so that was kind of a way you could approach these intramolecular aldol reactions. It's important to know that these reactions have the exact same mechanism that we've seen before. So same mechanism as before, but making rings. Okay, so one other thing that I want to add to our conversation about intermolecular aldol reactions is that you're more likely to make some rings than others, and that can pop up when you have non-symmetrical kinds of molecules. So if we chose a different type of a structure, So we're just going to make this very slightly different. So we'll choose a ketone. 1, 2, 3, 4, 5, 6. So still 6 carbons. So a ketone and an aldehyde now. Now I have a bunch of different possibilities. I have this carbon could become nucleophilic if I remove a proton. This one could, or this one could. And that means that, there's also 2 electrophilic sites here and here. So there's actually several possible products that could form. But it turns out that if you run this reaction, you're really only going to get 1. And that we'll see why in just a minute. So I'm going to actually add all my numbers now. So this is going to be carbon 1, 2, 3, 4, 5, and 6. So I can make some decisions about what kinds of rings will form very quickly without having to draw them all, just by looking at this numbering system. So if I connect the nucleophilic carbon that I've labeled 6 to the electrophilic carbon I've labeled 1, then I'll have a 6-membered ring. If I connect my carbon that I've labeled nucleophilic carbon 2, and I connect it with the electrophilic carbon that I've labeled 5, I'm going to have a 1, 2, 3, 4-membered ring. Or I could choose the nucleophilic carbon at 4 to 1, 1, 2, 3, 4. So there's 2 possible 4-membered ring products I could make, along with a 6-membered ring product. Which of those rings is most stable? Well, if you think about what you learned about ring strain last semester, you know that 4-membered rings are highly strained. And that means they're less stable. Remember that all of the steps of an Aldol reaction are in equilibrium with each other. And that means that if you ever did make the 4-membered ring, the reaction would just probably go backwards, and eventually you would funnel into the 6-membered product. So when you do this reaction, let's just use the exact same conditions. We could reliably predict that the 6-membered ring product will form. So I can start by drawing the 6-membered ring template, essentially a hexagon. I am going to choose carbon 1 to be here, and then I'll number clockwise. All right. So I know that I'm connecting carbon 1 to carbon 6, and that carbon 6 is adjacent to carbon 5. Carbon 5 will be a carbonyl still in the product, right? Nucleophilic piece will always have a carbonyl adjacent to it. And I know that rather than a single bond between 1 and 6, there'll be a double bond because I'm doing a condensation. So I have a product that looks like this. Okay, so there's other possible products. Plus 4-membered ring products. We're going to favor the production of more stable rings. Remember, because everything is in equilibrium, I'm just going to find that lowest energy state that I can get to, and I'm probably going to funnel all of my material to there eventually. So this will traditionally be 5- and 6-membered rings. Those are the most likely structures that are going to form. As you learned last semester, 3-membered rings or 4-membered rings, these are very, very unstable for ring strain reasons. And it turns out that 7-membered rings and 8-membered rings have similar problems. They're not as destabilized as 3- or 4-membered rings, but they're not great. So we're really going to focus on 5- and 6-membered rings. Okay, so I just want to reiterate that intramolecular Aldol reactions are exactly the same as the Aldol reactions and condensations that we've been seeing earlier in this video, but there's some special problem-solving strategies that I'd encourage you to use, especially numbering your carbons in a chain to start, because that will help you. It will help simplify thinking about what kinds of products that you'll need to make, and it will also simplify drawing the structures of those products. The trick here is to figure out where the carbonyl goes. That is, I think, the hardest part about these intramolecular Aldol reactions and condensations. And I think the way to do that is by making sure you look at your numbering carefully and knowing which of the numbers corresponds to electrophilic site and which corresponds to nucleophilic site. As you can see in both of these examples, if I find the nucleophilic number, so like 5, or in this case it would be 6, right? Then I know that I'm going to have a carbonyl next to that state, next to that carbon. That's always going to be true because of the nature of how these reactions work. So that concludes this video on essentially aldol reactions. And we looked at a bunch of different kinds of cases, but really this is about enolates reacting with carbonyl electrophiles. So in the last video of this SLO, we'll be looking at another wrinkle of the same concept, but rather than looking at aldehydes or ketones as electrophiles, we'll be looking at esters and other carboxylic acid derivatives.